This is the second video in section 7.4 on the topic of vectors. In the last video we saw a lot about how to work with vectors using pictures, drawing arrows tip to tail and whatnot to add or subtract or even to represent what a scalar multiple, a number times a vector, would look like. But in this video we want to expand that to how do we do math symbolically on vectors, like we do algebra, for example. And to do that, we first need to introduce this idea of representing vectors in component form. And so the idea here is that if I have any 2 points that sort of describe my vector by being its initial and terminal points, I can describe this vector by how far over in the x direction, that's this direction, and how far up I have to go to get from my starting point to my ending point. Those 2 numbers really define this vector, right? It's how far it goes in one direction and another direction separately. And so if I want to do that, if I want to figure out what those numbers would be, well, I just want to see over here in this picture, let me erase some of my doodling. I want to see that the x-coordinate here is x1 and the x-coordinate here is x2. If I want to know how far I traveled from x1 to get to x2, so I'm just thinking of this little portion of the triangle, well, that's just what's between x1 and x2. That is the difference of these 2 numbers. So that's why up here we have the distance from here to here is labeled as x2 minus x1. And so that value, how far we had to go to get from the initial point to the terminal point of our vector, how far we had to travel in the x direction alone, and how far we have to travel to get there how far we have to travel in the y direction alone to get there. Those 2 numbers are really the defining features of this vector. We can describe this vector completely just with those 2 numbers. So we say, put those numbers, x2 minus x1, the distance we had to travel in the x direction, and likewise y2 minus y1 would give you the distance you have to travel in the y direction to get to your terminal point. Just put those in a special sort of notation, these triangular brackets, we'll call those vector brackets, that indicates we are describing the rise with the y component and the run with the x component. x2 minus x1, y2 minus y1. Yeah, think of these as being like rise in the second component, run in the first component. It's like a slope, right? Defines a certain slope. Okay. So, and we should note here exactly what this is saying, that the vector notation, these vector brackets AB, is not the same as just parentheses AB. Parentheses AB is a particular location in the plane. Vector AB is a vector, a direction and a magnitude. So let's look at problem 6 here. Given vector V with initial point 3,8 and terminal point -1,3, find the component form of V. Well, so this is going to be easy. This is the exact setup that we had up here. Let's say our vector V is from this point Q, which I'll say is like, P, which I'll say is the 3,8 point, and Q, which I'll say is the -1,3 point. Now, if we want the component form of V, it looks like up here we subtract the x-coordinate of where we're going, that's x2, minus the x-coordinate of where we started. -1, x2 minus x1. So that's where we ended up, -1, minus where we started, 3. And this should be in vector brackets. Same for the y component, just subtract the y component or the y coordinate where you landed minus the y coordinate where you started. In this case, 3 minus 8. So you just subtract component wise. So you get -4, -5. There we go. That's the component form of V. Now, given vector v with initial point negative 12, 10 and terminal point negative 20, 10, find the component form of v. Let's see about this. Maybe pause for a second, see if you can do this one. Otherwise, I'm going to go ahead and jump in and do this one. So, initial point, that's like our p. Terminal point, that's like our q. Subtract where you're going minus where you started, component by component, coordinate by coordinate. Negative 20 minus 12, 10 minus negative 10. Oops. Which is just negative 20 minus 12 is negative 32. 10 minus a negative makes plus 20. So that's the component form of v. Now if v is placed with initial point at 5, 3, what is the terminal point of v? Oh, that's a pretty neat problem. So let's figure this out. So we're thinking of taking the point 5, 3 as our initial point p and saying somewhere else out here is our initial point q. Maybe I'll put it over here. And we know that the vector from p to q better be this vector v equals this guy, right? We just moved around where this guy was originally located. Originally we had its tail at the point negative 12, negative 10. Now it's at 5, 3, but we're still going over in the x direction and up or down in the y direction the same amounts even after we moved this vector over. We're just starting in a different place. So if we want to figure this out, what point q is, or what its coordinates are, we need to maybe give some labels to these. I'll say q as, let's even just label them this way. Let's call these x and y. Right. The coordinates of q are x and y. And we know the coordinates of p are 5 and 3. So then we just set up our equation, right? We know that in order to write down our vector v in terms of these guys, what we really have to do is write that where we're going minus where we ended up, x minus 5 and y minus 3, right? You subtract the coordinates where you're going minus the coordinates where you started. And I might have said that wrong the first time I said that. Where you're going minus where you started gives you your vector. Well, we know our vector better come out to be this v vector. That actually gives us two different equations we can solve. It says the y minus 3 must end up being 20, and the x minus 5 must end up being negative 32. So you can solve those. Pretty easy to do. X is negative 27, y is 5. So your point q must be negative 27, comma 5. Right, we solve for the coordinates of the terminal point there. Okay, so now that we have this ability to express a vector in component form, it's actually going to make it way easier to do kind of general mathematics on these, things like algebra, things we're used to doing. So let's start here at the beginning of how we actually do some of these operations on these component form vectors. Well, if we have two component form vectors, we actually saw that up here. We had a vector on the left and a vector on the right. Then the two are equal if and only if their corresponding components are equal. A2 is the A1 and B2 is B1. And that's exactly actually what we did up here. We equated the first components in one equation and the second components in the next equation. That's what we're going to say in terms of components gives us equal vectors. Both components have to be equal. We're going to say to add two vectors, again with components A1, B1 and A2, B2 respectively. To add the two, we're just going to add component-wise. You can show pretty easily how this follows from pictures, that if you go if you follow the displacement of one vector followed by the displacement of the other, overall you win a1 plus a2 units in the x and b1 plus b2 units in the y. So the sum of these two vectors turns out to just have the component-wise sum of the original vectors. Subtraction works the exact same way over here. Scalar multiplication, well, we just thought of these scalars as scaling the size of this vector. Well, if I know the vector went over an amount a1 and up an amount b1, if I want to scale that by a factor of c, I just multiply both of those numbers by c. And that's exactly what this scalar multiplication property for vectors is telling us. To multiply a vector by a scalar in component form, the scalar just goes to both components. Now, these properties of vectors are just saying that most of the mathematics you're used to doing on numbers also work on scalars also work on vectors. V plus W is the same as W plus V. C distributes across a sum of vectors. Zero scalar times a vector is actually the zero vector, which if you think about it would have components 0, 0. You can group sums in any order you want. You can add any two first and then add on the third. Vectors actually distribute across scalars. Scalar times the zero vector is the zero vector again. Adding the zero vector to something doesn't change it. That makes sense from numbers. When you have more than one scalar, you can multiply either one first. Right? These are properties that we're used to from numbers. We're saying they all hold here. This one's a little different. We don't have a real analogy for this in regular, well, maybe we do. If I have c times v in magnitude, that's just the size of v and the size of c multiplied. But since c is a scalar, then that kind of magnitude, the size of it's just its absolute value. And the v vector here needs a magnitude, a true magnitude. But then you multiply those together. And so let's see a couple of things we can do here. R plus S, given these vectors R and S, is pretty easy, right? R plus S just says add the components. 1 plus 2 from first components, negative 4 plus 3 from second components, there's 3, negative 1. Easy enough. Problem 9 here. You might want to pause. Now that you've seen how this is not going to be too hard, you might want to pause and do 9 and 10 on your own real quick. I'm going to jump right in though. Negative 4s is just negative 4 times the vector 2, 3. So this is a scalar multiplied on a vector. We saw a scalar multiplies to every component of the vector. This is negative 8, negative 12. Okay, 3r plus 2s, maybe a little more complicated, but it's really not bad. I should be putting vector hats on these vectors. This is just 3 times the vector 1, negative 4, plus 2 times the vector 2, 3. Well, we know how to deal with the scalars on each vector individually. The scalars hit each component. So it's kind of like you're just distributing the scalars through the vectors. It's not really distribution, but it kind of feels like it. Add the vectors component-wise now. First with first, second with second. You get 7, and negative 12 plus 6 is negative 6. So 7, negative 6. Right. Easy enough to do arithmetic on these guys. Now, what's really interesting is that there are some really useful other ways to represent these vectors on top of the pictures, on top of this vector bracket notation where we put the components inside. To see some other ways we can represent vectors, let's think of, let's define a couple things. First, a unit vector. A unit vector here, right? A unit vector is just any vector at all that has a magnitude of 1, a length of 1 when you draw that little arrow. So we can also define the magnitude of one of these vectors to just be the root of the sum of the squares of the components, right? Because if I have one of these vectors say AB looks like this, then we know, right, these are the components. We know the length of that guy has to be, by Pythagorean theorem, has to be root of a squared plus b squared, right? Because the vector components tell us how far over and up this triangle goes. It's a right triangle, so we apply Pythagorean theorem. We find the length of that vector is root a squared plus b squared. Well, now that gives us a nice way to find a unit vector in the direction of a given vector. That's a very common problem. Take a vector in one direction and give me a new one that's in the same direction but has a length of 1. This is called normalizing a vector. But let's see how to do it is described here, but let's see how to do it in this example. Maybe it'll make sense what these formulas up here are really describing. Okay, let's see. So let's find a unit vector u subscript w that's in the direction of this vector, negative 8, 15, and verify that it's a unit vector after you do it. So the process to do this is just take the vector that you want your unit vector to be in the direction of. This is my w vector, right? So this is my, let me give myself some space. This is my w vector. Take that vector and divide out all of its length. And technically you should be concerned. We're dividing a vector by a number. Remember, the magnitude of a vector, the length of a vector, is just a scalar. The length itself is just a number. And we're dividing this vector by this number. What does that really mean? It means that we are really multiplying it by the reciprocal. Same thing that division by a number always means. Multiplication by a reciprocal. And we can do this because we know scalar multiplication. We don't know scalar division. We've kind of just now shown that we do technically have scalar division if we think carefully about it. So this would be it. This would be our vector. All we're doing is taking this guy, which intrinsically has a length of 1, of length w, and divide out that length w. So once we have that, let's see what we get. We need to figure out the length of this vector so we can divide by the correct number. The length of our vector is negative 8 squared is 64. What is 15 squared? I'll give you a second to calculate. 15 squared is... Let's see, what does this come out to? I actually haven't calculated the final answer here. In that root, it looks like I have 289, which is the square root, which is the square of 17. So we're claiming that this vector, 1/17 times negative 8, 15, is in the correct direction, but only has a length of 1. And this makes sense. We've already shown, this was the length of that w vector. We have shown that that part turned out to be 17. Right, so w is some vector. We know the distance from here to here is 17 units. Well, if we multiply that thing by 1/17, we get a vector in the same direction, but 1/17 is long. 1/17 of 17 is 1. So this should be a vector that is 1 unit long in the same direction. Because we've taken 1/17 of the original length. Sorry, I'm writing tiny down there, I know. Not really important. But hopefully that makes sense. The thing was originally 17 units long. We didn't change its direction. We just scaled it by something that when we reduce this original length by that factor, it comes out to 1. So it's the reciprocal factor you need. It's 1/17 if the original length was 17. So that when you scale that vector down, the new length is 1. So we've gotten our unit vector. I claim that this is correct. And remember, the scalar does multiply into each component. So this is negative 8/17, 15/17. That's our vector. I'd say that's our answer, but we are also asked to confirm that it's a unit vector, right? Verify that it's a unit vector, which just means figure out the length of it, and it better be 1. Remember, the length is the root of the sum of the squares of the components. Which equals, let's see what we get here, 64 plus 225, both over 17 squared. Which is, you can do the math. We actually already did it up here. When we squared these and added them, we got that they equaled 17 squared. Right. So check. The length of this vector did end up being 1. This guy is a unit vector. Okay. So that's the general procedure. This is called normalize. What we just did was we normalized vector W to get the unit vector that we called UW. Make that clear over here. UW. All right. Okay. So now that we know about unit vectors, we can get on with this conversation about other ways to represent vectors. Well, it turns out there are 2 very special unit vectors that kind of serve as a way to describe all the other vectors. And we've got them represented here. These are called your book calls them, and they're pretty often called I and J. These are sometimes called the standard basis vectors. But these are just a unit vector in each of the x and y directions, if they were wherever they're placed, really. But typically we think of them as being placed at the tail of the origin. So this red vector is I, that points in the x direction, but is unit length. And this j vector is in the y direction, but with unit length. And so what we usually do is we actually can see that this vector, or this vector I, is just given by 1, 0, 1 unit step in the x direction, nothing in the y direction, so 1, 0. J is nothing in the x, but 1 in the y, so 0, 1. And notice if we have any vector AB, we can kind of decompose it into A comma 0 plus 0 comma B, because we saw how to add these back up. You'd take first component plus first component, A plus 0 is A. Second component plus second, 0 plus B is B. This is equal to what we just came from. And now we also know we could take that scalar A out of this one and take the scalar B out of this one, because remember, to put it back, it would just sort of distribute. A times 1 is A. The A times 1 is the A we started with. A times 0 is the 0 we started with. Likewise for this piece. But now all we really have written here is scalar A times 1, 0. That's the I vector, which we usually write like this. The little special hat, because it's a special vector. It's a unit basis vector. Plus B times the 0, 1 vector, the J vector. So any vector written in this form we can see is automatically expressible in terms of I and J. We would call this a linear combination. Of I and J. Right? Any vector can be written in this way. Instead of putting its components in these vector brackets, we can write it as A scalar multiple of I plus B scalar multiple of J. Your book calls the A value the scalar horizontal and the B value the scalar vertical components. You might hear those called X and Y components or first and second components. I've been calling them run and rise. Horizontals run, verticals rise. But this problem here, 12, is very easy. If we want to write negative 12, negative 30 in terms of I and j, it's just as easy as multiplying first component on the first basis vector, second component, let's think of it as this guy plus this guy, which we can drop the parentheses. 12i minus 30j. So negative 12i minus 30j is the same as this vector written in brackets. Negative 12, negative 30 in brackets. Exactly the same thing. Identical mathematically. Okay, so let's see. We want to relate the component form and direction and magnitude of a vector. So let's do something here. Let me clear some space and see if we can make sense of this. Well, actually, let's just work with the picture given. Given a vector in standard position, meaning tail at the origin, as drawn here, this vector v is our vector coming across here. Its direction angle is called, this angle theta is called its direction angle. It's measured the usual way that we measure theta, right? It's the same theta we saw in polar coordinates and trig. We always think of theta this way in mathematics. It's one of the very few very standardized things in terms of notation. So let's think about this vector. Let's think of this vector v as having components a, b in standard position, and we have this angle theta that gives the direction of that vector. It's measured from the x-axis as usual. Then notice if we just label the length of this vector as magnitude v, like it is here, we can describe both the x and y components, the horizontal and vertical components of our vector, how far over and up we have to go to get from start to end of our vector, with trig. Right? This side would just be magnitude of v cosine theta. Right? Let's see. This side here, this a value, well, maybe the easier way to say it is that cosine of theta would have to equal this a value, the length of this guy, over v, over magnitude v, the length of the hypotenuse. So multiply this over, get rid of it here. A equals magnitude of v cosine theta. In the same way, the b value is just magnitude of v sine theta. Right? And we get these expressions here. All this is telling us is that if we want to take our vector, which we said, where were we? Yeah, it was up above. If we take our vector AB, if we kind of pull all of its magnitude out front, it's just going to leave behind. Let's do it this way. Let's replace AB with what these formulas here tell us we have. Length v times cosine theta, length v times sine theta. Then I can pull that scalar length magnitude v out front, and it just leaves this vector cosine theta, sine theta. And notice we've pulled all the length out front of this guy. If we were to take the magnitude, let's do this just to see something. If we took the magnitude of just this vector part that remains, we took all that scalar length out front, but this vector part remained. Let's take the magnitude of that vector part. Remember, it's the root of the sum of the squares. Well, look what we get. Cosine squared plus sine squared is 1. We get the square root of 1 is 1. This guy, when we take its length, is 1. This is a unit vector. So somehow we've seen that we can split up a vector into its length out front, all multiplied on a unit vector in the correct direction, just given by this angle theta. Right? All the length is tied up in the scalar out front, but that angle theta controls the direction, which we express in this unit vector. So it's like we hone in what direction in the plane we're going in, then we give all that magnitude to it out front. Right? This is a very useful way to decompose a vector. So let's see these problems 13 and 14 here. Write the vector v in the form ai plus bj, where v has magnitude 10 and direction angle 3 pi fourths. Okay, easy enough, right? We know from what we said above, we can write it as this vector, where our magnitude in this case is 10, and our angle theta in this case is 3 pi fourths. You might say, why aren't you going to the ij form of this right away? It's because I prefer to work in vector brackets. At the end, though, it's really quick and easy to transfer out to the I and j form. So really you want to be comfortable working in both, but I think most people have a preference. Now, cosine of 3 pi fourths, sine of 3 pi fourths, those are special angles, so we can evaluate those real quick. Cosine gives me negative root 2 over 2. Sine gives me positive root 2 over 2. And notice here I have the same component in both places. I could actually factor that out front. I say factor, remember it's not really factoring. It just looks kind of like it. And we would leave behind negative 1, 1 inside the vector. That allows me to make some simplifications here. I get that the magnitude times the direction vector ends up being this. I don't know if it was worth factoring things out, but let's actually see how we can unpack to the ij form we want. Just see what we've got in both components. Those are what we need on the I and the j. That's it. Right, so starting out here, this is pretty easy. If I have the direction angle and the magnitude, it's easy to write this stuff down. Let's do it backwards here. It says, let's find the magnitude and the direction angle of this vector s, 7, negative 3. All right. So we might want to write it in whatever form we prefer. I like vector brackets, so maybe I write it in this form. Or if you're happy with this, that's fine too. But either way, we want to identify that our x component or horizontal component is 7, our other component, our y component, is negative 3. Right away from that, we can find the magnitude. Magnitude s equals root of the sum of the squares of those components. Looks like 49 plus 49 in the root is root 58. What's that divisible by? I don't know. Not divisible by 4. Yeah. I think we're just going to leave it like that, root 58. So we'll say that's our magnitude of this vector s. It's root 58. But what about the direction angle? Let's think about this. We have a vector where in standard position, it would look like it goes 7 units in the x and negative 3 in the y. That's what our vector looks like, roughly. And the direction angle is this angle. Well, we're going to take one from 0 to 360, so you're used to doing this. We'll go all the way around instead. That guy's our direction angle. We'll look at this, I'll call it theta prime instead. So let's see if we can find that theta prime. Well, we know right away this edge of the right triangle here is like a -3. This leg of the right triangle is a 7. We know the hypotenuse is √58. We can do a little bit of trig here and figure out that angle using some inverse stuff. So maybe I do a tangent. We can say tangent of theta prime, that I'm calling it, is opposite over adjacent. Right? Opposite over adjacent. That means theta prime is tan inverse of this. So let's see, I haven't computed this. Let's see what I get when I do. Tan inverse of -3/7. I get -23.2 roughly. Right, so that's this angle, but we are asking for an angle between 0 and 360. So measured this way around, oh, what's that going to be? Let's just go the full 360 minus this 23.2 will leave us with the original value. Just think of adding 2 pi to this. That's the easy way to think of it. Oops. Let's call it 360 degrees. And what do we get when we do that? Let's get it right. Let's see. Oh, I got 336.8. I should say this is approximating the theta prime value here. Okay. So we found the direction angle, and we found the magnitude. All right, so not too bad. Well, let's look at a couple of applications. I think this is where we'll wrap up. Let's just do a couple of these little application problems. This problem 15 says a ball is thrown with a speed of 65 miles per hour at an angle of 12 degrees from horizontal. Write the velocity vector at the time of release in terms of I and j. So we know, let's think of this as our velocity vector when this ball is initially released. We know it's thrown at a speed, a scalar version of how fast something moves or how something changes position, at 65 miles per hour. That tells us that the magnitude of the velocity, that is what speed is. It's just how big that velocity is, regardless of the direction. Speed just has the scalar value of its magnitude. In this case, it's going to be 65 miles per hour. And we're told the angle of elevation above the horizontal is 12 degrees. So we can do this pretty easily, just like we did the last one. We want this in terms of I and j, right? So let's do this one a little more directly than the last. Still just using those formulas we saw above, though. Right? These formulas saying that we can express any vector in terms of its magnitude times cosine of its direction angle in the I direction, plus its magnitude times sine of its direction angle in the j direction. So that's exactly what I'm writing down here. This is pretty easy from here. 65 is the magnitude. 12 degrees is the angle, right? Just from our picture. Oops, sine. So let's see, I'll do a little calculation here. I get to the nearest tenth, as indicated or as asked, I get 63.6 miles per hour in the I direction, plus 13.5 roughly in the j direction. And we did round these values, but you could check that the magnitude of this vector should be 65 at the end of the day. Okay. Just one sec. Yeah, I wanted to check that. It does come out to the nearest decimal place, to 1 decimal place. It comes out accurate when you check that magnitude. It's a good way to check your work. Go ahead and check out that 63.6 squared plus, oops, pardon my handwriting. The magnitude of that vector does come out really close to 65. It does work out. Okay, so this vector describes that ball's velocity right when it's released. Most of its velocity is in the horizontal direction, which makes sense from the picture, but a little bit of that velocity is in that vertical direction, giving it that little pitch upward at 12 degrees. Okay, last problem here. I know it's a long video. Appreciate you hanging in there. I think this would be a good time to pause, try to do this problem on your own without knowing much about it. I think you probably could figure out what some of these words mean if you just guess, but let's go through it. If you do want to pause, do that now before I get through the solution here. Okay, let's give this a shot. Now we're going to talk about vectors representing forces, which if you think about it, makes sense. A force is just a push or a pull in physics. You can think of it that way. And we want to think of a force as being something that has a certain direction that you push or pull in, but also you can push or pull with different magnitudes, with different strengths. So certainly it should be describable by both a direction and a magnitude. It should be describable by a vector. So we're going to look at a couple force vectors here. 10 in the I direction, -3 in the j, -2 in the I, 1 in the j, and finally this last vector, F3, is just 11 in the I direction. And we're saying all three of these act on some object, pretty common sort of situation in physics. Find the resultant. And I mentioned this briefly in one of the previous videos that when we talk about vectors representing forces, we say the resultant is the sum of those, just overall what those forces come out to if we put them all together. So this is just asking us to add all these vectors that were given to us. And we're going to see this is very easy. You could write this first vector as 10, -3, -2, 1. This one might be a little strange. It certainly got 11 in the x component, but nothing in the y component there. So I'll just leave that one as a 0. Well, we could add with the I, j, and k, or with the vector bracket notation. I think we've seen this with the vector bracket, so let me show it with the I, j, and k. Vector F1, I'm just copying down from here. It's 10i minus 3j plus F2, so plus -2i plus j. And finally, F3 is just plus 11i that I'm adding on. And now you can handle this algebra to simplify this just as if I and j were any other variables, any other symbols that you could use algebraically. Collect all the I terms. We have 10 of them minus 2 of them plus 11 of them. 10 of them minus 2 plus 11 of the i's. Collect the j's. -3 and +1. And put them together. 10 minus 2 is 8. 8 plus 11 is 19 in the I direction. Looks like we have -2 in the j. Right, this is our resultant force. You could express it in this notation, Or you could figure out the magnitude of this force, right? Which is probably a pretty important thing to understand. If all these forces are acting on the same object, knowing how much force overall this thing's experiencing might be an important idea. That would be the magnitude of the resultant. We weren't asked to do these last couple parts, but this last part, but I'm going to do it anyway. 19 squared is 361. 2 squared is 4. It's root 365. Which I don't think simplifies down. Right, but that's in root 365, which is roughly 19.1. We know at the end of the day, this is 19.1 pounds of force that this thing is experiencing, with all these different forces put together, canceling and complementing each other. Overall, it cancels out to 19.1 pounds. Maybe if we were being really careful, we'd label each component pounds. I wouldn't knock you if you didn't, though. What additional force F is needed for an object to be in static, for this object to be in static equilibrium? Well, what does this mean? That's the big question. Static equilibrium, using impressively strange words here to make this seem way more complicated than it is. Static equilibrium just means the object isn't moving, which means it's not being pushed or pulled at all. We said forces are pushes or pulls. If we're not being pushed or pulled at all, overall the forces we're experiencing must be zero. There's no push or pull. We're in equilibrium. We're not moving, not being pushed or pulled. So if we're going to add one force in to make the sum of all these zero, then let's just look at what we can say. We can say that F1 plus F2 plus F3, we know that equals, these are all my forces, that equals our resultant vector here, 19, negative 2. Right? And so we're asking, what could I add in to this set of three vectors so that at the end of the day, what could I add in so that I get the zero vector? Everything cancels out to zero. Well, this is pretty easy to solve. Just take this equation on the left and subtract the r vector to the left side. Subtract it from both sides to cancel, to balance the equation. R minus r here, that's just the zero vector. So we've figured it out. What needs to go here to make the sum add up to a total of zero? The resultant of these, but with the negative in front. Right? That's what we need to add in. Right? To satisfy this equation, that question mark has to be the negative of the resultant. So what additional force F is needed? That additional force should be negative of the resultant, which is negative of this 19, negative 2 vector. The negative looks like it distributes. It just goes to each component separately. So that's our solution. That's the vector F that would put us in static equilibrium. That's the force that would kind of balance out all the other forces. Right? Okay, that's the end of this video. More next week.